Okay, so the last topic in chapter 28 is about the torque on a current loop. Okay, so this is quite important. So this is similar to putting an electric dipole in the E field. Okay, so here if we put a magnetic dipole in a B field, okay, so the motion will be similar. Okay, but we use the B field, the magnetic dipole more frequently in our daily life. Okay, so it is related to the electric generator and also the motor. 就是这个是那个马达的话就是用这个原理的是用这个原理，或者是发电机的话就是这个原理的类似，但是是有点相反的感觉，Okay, so here so here it says as shown in the figure, the net force on the loop is the vector sum of the forces acting on its four sides and comes out to be zero. The net torque acting on the coil has a magnitude given by this one. Okay, so here, okay, so we try to generate a uniform B field. Okay, uniform B field as indicated by these green arrows. Okay, by these two magnet bar. Okay, big magnet bar. So it will roughly generate B field in between, something like an energy to the capacitor. 就是类似那个电容的话，有电荷它就会产生均匀电场这个也类似的。Okay, so here we try to fix a coil here. Okay, fix a coil here. So it cannot move, but it can rotate. So here, if we provide a current, okay, like this, okay, in this case is counterclockwise. Okay, so you need to distinguish what is clockwise and counterclockwise. 就是因为有时候考试的时候会问你什么那个电流是顺时钟反时钟 ，clockwise 是顺时钟 ，counterclockwise 是反时钟。因为其实很好记的 ，counter 就是反嘛，就是你就算物理不会的话，你玩那些什么游戏，它也会有反击嘛 ，counter attack 嘛，就是 counter 就是这个反嘛 ，OK， 所以一个是顺时钟是 clockwise 嘛，反时钟是逆时钟是那个 counterclockwise 嘛。Okay, so here we have a current in counterclockwise direction. Okay, so in this case, just now we already learned that there will be force acting on it. Okay, so which is the second version of the Lorentz force. So actually here, we can simply verify that there will be forces acting on them, and then actually say this force and this force actually point to opposite direction, and so as these two. So the net force on the whole thing is zero, so that it cannot shift. But it can rotate. It can rotate. There will be a torque on it. So let's see. Okay, so let's say for this wire, the current is in this direction, so which means the L is also in the same direction. And then the B field here, we assume it is pointing to the right side. So it is like the L is pointing out of the page and then cross to the right side. So your thumb is pointing upward. Okay, so this is the direction of F. And then here the current is like this. So as the L is pointing to the same direction, so B is pointing into the page, and then your finger crossing to the right side, so your thumb is pointing upward, pointing downward. Okay, 所以记得要用右手定着 right hand rule 我们一定100%、10000%是用右手定着的不会用任何时候都不要用左手。还有的话，这个图的话就是有一点 立体的感觉，所以其实这个就算好像看起来是有点角度，其实你要想象它是往外的，就是垂直这个平面往外的，不然的话你想象它是斜的话，那你很可能会搞错，很可能会搞错，就是你要把这个立体图转成一个比较容易理解的方向，你就会比较不容易出错。Okay, so actually here we can see that this F and this F actually point to opposite direction. Okay, so in that case, if it is a rotational axis, then there will be a torque. There will be a torque. The torque is actually the torque is actually in that direction. So it also follows the right hand rule. Okay, how this right hand rule is like? So actually this force is pointing upward. This force is pointing downward. So you will expect this coil will rotate clockwise. This will rotate clockwise if you see it from this direction. Okay, it is rotating clockwise. So the right hand rule is like you use your finger, follow the rotational direction. Okay, then your thumb will be pointing to the direction of the torque. Okay, so this is the right hand rule. Okay, this is also the right hand rule here. Okay, so we always use the right hand rule to determine the direction. So the torque is actually pointing to that side, actually into the page. Okay, so here is actually said that this torque is NIAB sine of theta. NIAB sine of theta. So the idea is like, so here we have previously we have IL cross B, and then, so this is the Lorentz force. So this N is the number of turn. Okay, this N, capital N is for number of turn. Okay, you need to pay attention to whether it's a capital N or small n. Later on, there will be small n. So we always use the capital N to specify the number of turns, and the small n means the number of turn per unit length. 就是线圈的密度是用小写，那总数是用大写啊。之后2降到3降或是都会继续用这个大 N 代表总数，小 n 代表密度。Okay, so in that case we have for the torque we have the distance. We have the distance of this force between the force and the rotational axis. So and then we have both sides. So actually for the length, for the arm of this torque, and then with these two force, so actually it also includes this height of this rectangle. So this height of this rectangle multiplied by the L become the cross-section area. The cross-section area of this rectangle. Okay, so it is actually tau equals NIAB sine of theta. Okay, sine of theta is actually the angle between the L and the B field, I and the B field. Or the angle between the B field and the vector to the and the normal vector to the coil. The normal vector to the coil. So for the normal vector of the coil, we also use the right hand rule. Okay, as much as the current is rotating in this direction, so your use of finger follow the direction of the coil, and then your thumb is like this. So this is the normal direction. This is the normal direction, perpendicular to the coil. Perpendicular to the coil. Okay. So this is tau is NIAB sine of theta, And here we try to define something called the magnetic dipole moment. Magnetic dipole moment, similar to the electric dipole moment. Electric dipole moment. So originally, the electric dipole moment is like P equals Q times D. Okay, if you still remember. Okay, suppose we have two charges with the same magnitude but opposite in sign. So plus Q and negative Q, and then this is the D. Okay, this is the D. So the electric dipole moment is like this. So analogy to this, OK， 就是跟这个类比，就是把 electric dipole moment 变成 magnetic dipole moment 的话，就把 Q 变成 I， 然后把这个 D 变成面积啊，就会变成这个magnetic dipole moment. Okay, so actually you can regard it as a definition. Okay, but here we also have the number of turns. Okay, the number of turns for the coil. Okay, so it's just a multiplication there. So in that case, if we have mu equals NIA, so which means this stuff becomes mu, and then it becomes tau equals mu b sine of theta. Okay, and the theta is the angle between the mu. Okay, so the mu also takes the direction of the normal vector. So which means that this is also the direction of mu. This is also the direction of mu. Okay, also follow the right hand rule. You use your finger follow the direction of the current, and then your thumb is pointing to the direction of the magnetic dipole moment. Yeah. So actually, this is okay. So this is nothing but tau equals mu cross b. Okay. So yes. So what is? So the tau is the cross product between the magnetic dipole moment and the B field. And similarly, we have the potential energy, the orientational energy, or the potential energy U theta to be negative mu dot b. So back in chapter 22 or chapter 23, I don't quite remember, you also have the tau equals P cross E, something like this, and then U of theta equals negative P dot E. Okay, so this is just an analogy, 就是两个电场磁场的类比，它们有一样的公式，所以你们可以把它看作是像类似的东西哦 ，magnetic dipole moment 跟，因为他们取了同一个名字了，所以你可以想象它们是一个很相似的特性。所以这里的话就是代表说，如果你把一个 magnetic dipole moment 放在一个磁场外部磁场里面，如果有一个角度的话，它就会晃来晃去。或者说什么叫做 magnetic dipole moment， 就是一个最简单的 magnetic dipole moment 就是一个 coil， 它有电流啊。So actually the definition of the magnetic dipole moment is nothing but you have a coil, you have number of turn, you have number of turn to be capital N, and then you provide it a current. Okay, you provide it a current, and then the cross section area. Okay, the area enclosed by this coil will be A. So with this structure, okay, like for example like this or like this. Okay, it's already a magnetic dipole moment. So which means 就是有一个线圈，你给它电流，它就已经是一个，它就是一个磁偶啊，它就是一个 magnetic dipole 啊。那这个 mu 就是 magnetic dipole moment， 就是它本身叫做 magnetic dipole， 或者是这个本身叫做 electric dipole 啊。那它这个物理量 P 或者这里的 mu 啊， 就是所谓的 dipole moment 才是那个 O G 哈，我不知道怎么念。Okay, so here is just to remind you that, uh, okay, so if you have a coil like this, the current is counterclockwise. Okay, you use your forefinger follow this direction. You use your forefinger follow the direction like this. Your thumb is pointing downward, so the magnetic dipole moment is pointing downward. And in this case, you use your forefinger follow the direction like this. Your thumb is pointing upward, so the magnetic dipole moment is pointing upward for that case. Yeah, so here we have a sample problem. So here it says a circular coil with 250 turns and area A and a current of 100 μA. The coil is addressed in a uniform B field with this magnitude aligned with B. Okay, so like this. So we have a number of coil and then with a current. So the magnetic dipole moment mu is aligned with the external B field. So in the figure, what is the direction of the current of the coil? Okay, so the current is roughly like this. Okay, so it is hard to draw because yeah, it's already a 2D graph. Okay, it's just like a cross section. OK， 所以就是它从里面往上的外面出来的，因为它是一个线圈呢，其实它是一个圆柱形的啊。不过往里面的那一层是往上的，往外面那一层是往下的，所以我大概画成这样。OK，so like this. OK， this is the direction of the current. Okay, so for question B, how much work would the torque applied by an external agent to have to do on the coil to rotate it 90 degrees from its initial orientation so that mu is perpendicular to B and the coil is again at rest? Okay, so at this stage, the potential energy here is minimized. You can consider it's a very small number. In that case, we don't call it a zero because yeah, in this case we have a dot product here, so it means it is like negative mu b cosine of theta. So this cosine of theta range between -1 and 1. So the minimum value will be negative mu b, and then the maximum value will be positive mu b. Okay, so this is the case, and if it is zero, so it means if theta equals 0 degree, cosine of theta is 1. Okay, so it takes the minimum value of negative mu b. Okay. But if it is theta equals 180 degrees, then cosine theta is -1. It takes the maximum value of mu b. But if it is 90 degrees, then it is 0. So in that case, we have a WA. Okay, will be U 90 degree minus U 0 degree, which will be negative mu b cosine of 90 degree minus negative mu b cosine of 0 degree. Okay, so this is nothing but 0. Okay, this is 1. So finally it becomes mu b, so which will be NIAB. Okay, so mu is NIA. Okay, so we have a number of turns to be 250 times I is I is 100 mu, 100 times 10 to negative 6. And then A is 2.52 times 10 to negative 4. And then times 0.85 equals 5.36 mu J. 5.36 mu J. Okay, I forgot to change it back to blue. Okay. 红色还能看到吗？我就不改回去蓝色，因为以前上课有试过，我不小心写成红色，学生说他色盲看不到红色。Okay, it should be on the next page, but yeah, it doesn't matter. Okay, so